Why is 5% accurate?
It could be 5%, 1%. It is provided by the manufacturer.
What's the source? Why it has? Why
You see, for example, if it has a strain gauge, you put mass on the balance, it may have a strain gauge. The gauge is being compressed. How much is it? Now that compression strain is being converted into a voltage. There is an amplifier in between. That amplifier has an accuracy. So it depends upon the construction of that particular device, and this has to be provided by the manufacturer.
It's also like the response time of the
Yeah, it's not response. It is every instrument is going to be accurate up to a certain extent, and then you calibrate it.
It depends on the material which he has used. That's why the balances are 500 rupees, 10,000 rupees, 1 lakh, 5 lakhs. The same balance, same shape. It goes to 10 lakhs.
Exactly.
It depends on the material which he has used.
So there are balances that can be extremely sensitive but highly inaccurate. So there are different sources of uncertainty. So if 0.1 is due to the digital accuracy, and if 1% of this is 0.5 roughly. 1% of 50 is 0.5. So there's 0.1 due to the least count and 0.5 due to the rating of the instrument, the instrumental accuracy. This is accuracy, this is the precision. Now both of these uncertainties contribute. Now would you like to add them up to find the total uncertainty? There are different procedures. If this is much larger than this, you can take the bigger one. If they are comparable, you can take, naively you would take the sum. Naively means the first impression, let's take the sum. But this could be positive, this could be negative. So sum is not good, you are overestimating uncertainty. So good thing is you take the square of this, and take the other. This is adding uncertainties in quadrature. It's just like Pythagoras theorem. Okay, this comes out from probability theory. So if I take this uncertainty 0.01 plus 0.25, I get 0.51. This is 0.51. Now I only want to keep one significant figure. I don't care about this one because in the uncertainty is only one significant figure is important. So 0.5. So this becomes 0.5 gram. This is the mass of 5 magnets. This is the best estimate of the mass of 5 magnets, and this is the uncertainty in the mass of 5 magnets. Up to 68% confidence. Now I want to find the mass of one of them. I divide this by 5. 1, 1, 3. Plus minus, I divide this by 5. Because every uncertainty leaks into any derived quantity by the Taylor formula. I will explain that in a minute. So I divide this by the uncertainty by 5 as well, like we did for stopwatch. We took the oscillations in 10, found out the uncertainty in 10 oscillations, then we divide the uncertainty by 10. Here we dividing the uncertainty by 5 because we have 5 units. Yeah, 0.1. So this is the uncertainty in the mass of one magnet. Now this M has, if I put 11.3 here and I put the best estimates of H, mu and the slope, I get the best estimate of the field. But what's the uncertainty in B? This uncertainty in mass will leak through into this result. Okay? This is going to leak through. If I measure X and I want X over Y, this is Z. What if X has an uncertainty and Y has an uncertainty? This will be uncertain. So the formula that we use is the Taylor expansion. which means that if I have z, which is a function of x and y, say z is a function of two variables, x and y. I want to find, for example, z equals x over y. One example. If I want to find the uncertainty in z, then what I need to do, I need to find the derivative of f with respect to x multiplied with the uncertainty in x, okay, plus the derivative of f with respect to y into the uncertainty in y. And if there are more terms, you do it for all the terms, x, y, k, j, everything. Now what is this telling us? Uncertainty in z depends upon the uncertainty in x and the uncertainty in y, but not by the same amount. The weightage that you give to the uncertainty in x is how much does f vary with x. If this derivative is large, it means that this is a prominent uncertainty. Right? If this is large, f depends more upon x. It means you have to give more weightage to the uncertainty in x. Right? So the uncertainty in x will have a prominent effect in the final uncertainty. So this is the Taylor series expansion. If you do the Taylor series expansion about a point, this is the lowest order term. Then you have other terms, partial square f, partial x square, ux squared, etc., etc. So this is the uncertainty. So we use this formula. Now if we have an uncertainty here in the mass, this is going to affect the uncertainty in the field. So let's find
u over v, derivative of u over v formula. So in between you can have minus sign.
it's the same, that comes from here. This is a more general formula.
You can take minus sign. Here using u over derivative of u over v.
This could be positive, this no, this I don't understand the question.
If the function is x over y, in derivative of x over y, you cannot express by using the formula u over v.
Okay, let's find this. If this is our function, let's find the uncertainty in z. Okay.
We have like four things which have uncertainty, right? So it's going to be the product of two uncertainties in the numerator and product of two in the denominator.
Right. Let me first answer the question. So if z equals x over y, I know that partial z over partial x is 1 over y. I know that partial z over partial y is minus x over y squared, right? Now the uncertainty in z, if this is my formula, if I am applying this formula, my uncertainty in z is this thing 1 over y into the uncertainty in x, ux, plus this thing is minus x over y squared, the uncertainty in y. So for any value of z, my uncertainty will depend upon y and x. Okay, so this is my uncertainty in z if this z equals x over y. So I apply this formula to this particular. Now I have this. I have an uncertainty in m, un, I have an uncertainty in h, I have an uncertainty in this thing, in the moment, u mu, I have an uncertainty in the slope. So I have an uncertainty in all four of these quantities. And all four of these quantities will contribute to the uncertainty in B. Now how do you find out the uncertainty in B? First of all, you need to determine the uncertainty in each one of them. This is easy. We've already done this. This can be done. We measure the height with a vernier caliper and do the uncertainty analysis. We know the uncertainty in the moment. It's given in the problem. The slope is uncertain, right? And in your dossier, in your bags, there is a sheet that gives you the uncertainty in a slope formula. There's a sheet of uncertainties. Okay? So you can find out the uncertainties in the slope. Now what does the uncertainty in the slope mean? If I have a graph, if these are my points, I can draw a line like this, right? But what's so special about this line? This is the least squares fit. What's special about this line? Can't I draw another line? I can draw. Why couldn't I draw this line? This is another line. To the eye, it appears that the yellow line and the blue line should be equally good representatives. So there's something special about the yellow line. Does anyone know what's special about the yellow line? What is meant by a least squares curve fit? Exactly. What it does is that if at each point I take the deviation of the point from the line, these deviations, I take the square of each one of them and sum them. The yellow line minimizes the sum of the squares of the deviations. It minimizes the sum of the squares of the errors. So the least squares curve fit. But there's no reason why this line cannot be uncertain. The blue line is also some other inhabitant or from another planet can come and say, this is not a good measure. This is not a good measure. The minimization of the least squares error is not a good measure. He or she might draw another line. So this slope, you can draw different lines. So there is an uncertainty in the slope. And the formulas are provided to you in a sheet. Over lunchtime, you can look at the contents of your bag. Okay? It's a good time to do that. There's an uncertainty in the slope, which means you can draw lines with different slopes. And then each of these lines will intersect this curve at a different point. So there's an uncertainty in the intersect as well. And that formula is also given. So each one of these has an uncertainty, and with the help of this formula, we can differentiate this B with respect to M, with respect to H, with respect to mu, with respect to slope. It's a closed form, and then we can use the formula that I wrote, and then find out the uncertainty in B. My advice to you, or sorry, I cannot make an advice, I'm using wrong, but my suggestion to you is once in your lifetime, if you haven't done this before, only once in your lifetime, do one experiment in your life which actually goes through the entire process of finding out the uncertainties and calculating the uncertainty in a derived quantity like the one we have over here. Just once in your life, just for the sake of it. Our experiment was easy because you know that each time period had an uncertainty. Each time period has an uncertainty. Which means, okay, let me redraw this graph. Just last 2 minutes and then we go for lunch. One question. If my uncertainty in I have a cube of length 1 centimeter. If the of 10 centimeter, each side is 10 centimeter. If the uncertainty in the length is 1 centimeter, what's the uncertainty in the volume? 40, right? So 3 times E equals L cube. So if the uncertainty in the length is 1 centimeter, the uncertainty in volume is 3 centimeter. Derivative of this, 3F. If the uncertainty in volume is 1 cubic centimeter, the uncertainty in length is 10 to the power minus 3. Okay, so uncertainties go from basic quantities to derived quantities. Now our result was nice because we have n here, we have n square here, and we have t square here, and we have these points. Now we know that the time period, each time period had an uncertainty. We know that, right? So each time square will have an uncertainty. 2 times is 0.2 seconds. So I can draw error bars like this on each point. I should always draw error bars. These error bars, by luck, are the same on each one of these points because of our experiment. Is there any uncertainty in n squared on the x-axis? No. For this nice experiment, we don't have an uncertainty here. But in general, you might even have an uncertainty in the x-axis. So in general, you might have an uncertainty here as well. So how do you, if you want to find the slope, first of all you would like to transfer this uncertainty in the x-axis to the y-axis. So this is slightly more complicated. If you are interested, when you do the real experiments, we can look at it. So this is one thing you need to consider, uncertainty in the independent variable that has to be transferred to the dependent variable. It's also possible that one of these uncertainties is large. So these two uncertainties are large because of our experiment. Low values of current, the uncertainty is large. Very high values of current, the instrument is not behaving properly, it's large. It's very possible. So now if you would like to do a fit, the fit should not keep this point and this point on equal footing, because this point is a large uncertainty. The fit procedure, the algorithm, should give less weightage to this point. It should give more weightage to the points who have smaller uncertainties. Is this making sense? So any point that has more uncertainty is likely to will affect the result, will increase the uncertainty of the final result. So because of some instrument which behaves differently at extreme values of current, voltage, or you see Young's modulus experiment. If you extend the string too large, the Hooke's law breaks down. If in this experiment theta is too large, you would like to give less weightage to those points which have large magnets attached to them. So you do not want to treat all of these points on equal footing for your curve fitting. So you give less weightage to the points with the uncertainty. So your measure of u squared 1 over u will give a weightage to each point in the minimization procedure. But these are more technical stuff. Our students in the first year in a semester-long course learn about this. But these are things to keep in mind. And I would like to finish here just by reminding you that at least once in your life, as teachers or as students, we should go through the complete process of the nitty-gritty of uncertainties. Even if we sweat, even if it's tiring, we should go through this, because this is going to give us confidence in teaching to our students. So now what we're going to do, we're going to break for lunch. The lunch is in the Pepsi Dining Center. It's just around the other building. You have coupons, and we'll reconvene here at 2 p.m. and then we'll start performing some experiments. Inshallah. Thank you very much.